In this section, they start the lesson just talking about basic function operations. So here they are, and I want you to pay attention to the notation that they use, because we will use the same notation that you see here, okay? But yeah, it's very trivial, that if you have two functions, you can add them, you can subtract them, you can multiply them, you can divide them. So go ahead if you'd like, just to take a couple minutes just to look over examples 1, 2, and 3 on page 107 and 108. We'll look at example 4, mainly just to talk about domain. Okay, so here's example 4. So they give you two functions. F of x is radical x, and g of x is radical 4 minus x squared. And they want us to find the quotient of each one in addition to its domain. So actually this is fairly trivial as well. So f divided by g of x is simply f of x, which is radical x, over g of x. Okay, so when you consider the domain of this function, you have two square root functions within the function. So each square root function has its own domain. So for the top one, we know that x has to be greater than or equal to 0. For the bottom one, we know that 4 minus x squared has to be greater than or equal to 0. And actually, it could only be greater than 0. It can't be equal to 0 because it's in the denominator, right? You can't divide by 0. So if you were to solve this out, you will find that x has to be between -2 and +2. Okay, you could work that out. Now, if you superimpose both of those graphs on one number line, okay, so here's -2 to 2. And so you'll see that the blue one goes from here to here, so that's the domain of the blue one. And the red one starts here and then goes to the right. So that's the red one. So where do they overlap? Well, they overlap from 0, inclusive, because it's included in both, to 2, non-inclusive. That's where they overlap. So therefore, the domain of this function is 0 to 2. Okay, if you look at the quotient g divided by f, so that's going to be the reciprocal. So this time, the domain from the numerator, let's box that, we know it can equal 0. So in this case, our domain is going to be this. But for the denominator, x has to be greater than 0, but not equal. So again, if you consider these two graphs superimposed on top of one another, right, you've got the red one that includes both sides and goes from there to there. Then you've got the blue one, which is open on 0 and goes to the right. So the overlapping part is open 0, close 2, shaded in the middle. So here, your domain is 0 to 2, like that. Okay, next, let's talk about composition of functions. Okay, so here's the official definition of a composition of a function. The way that I would like to discuss this with you is, if you recall, we talked about how, sorry, that's really ugly. If you have a function, it's like a machine, an input-output machine. So, for example, let's say we have this machine where you input x, this is the g function, okay? So the output is g of x. Now, suppose that output becomes the input to another machine. So we'll call this machine the f machine. Then the output would be f of g of x, right? So that's the composition of functions. So the idea is, here you have a situation where an input has to go through one machine, produce an output, and then that output has to go through another machine and then produce another output. It's kind of like an assembly line, right? So if you, let's say you own a business and you're producing some widget or whatever. And the way you produce this widget is first it has to go through the G machine, and then the output of that has to go through the F machine. So it's like first step and second step. However, suppose you were able to come up with another machine that does both processes, so that the original input X only has to go through one machine to produce the final output. So I can illustrate that, and this is going to be really ugly, so I apologize. But let's say you have this other machine. Okay, so now this other machine is what we call f of g. And so X goes into f of g, and in one fell swoop gives you the same output that you would get as if you were to go through these two other machines. So if you're a business owner and you can come up with this machine that does multiple processes, you could potentially save time, which of course means that you could potentially save money. So, I mean, this is a really crude example, but this is the type of thinking that goes into, streamlining a business, production, mass production of products, things like that, is that you want to be able to make things as simple and as cost effective as possible. So composition of functions is kind of a way to do that. Okay, so the idea then is that regardless of which way you go when you start with X, whether you go through the composition of functions or you go through one step at a time, that you produce the same output. Okay, so that was a lengthy discussion. Let's look at example 5 together, and I'll show you how this works practically. So they give you two functions. The F function adds 2 to the input. The G function squares it and then subtracts that result from 4. So first they want us to find what is f of g of x. Okay, so f of g of x simply means that you're putting the g function into the f function. Okay, so the g function is 4 minus x squared. So you put 4 minus x squared into the f function and you replace x. Right, so when you do that, the x, this x right here, becomes 4 minus x squared and then plus 2. So if you simplify that, that's 6 minus x squared. Okay, so f of g is 6 minus x squared. Okay, pretty basic. Now if you go the other way, let's see, where's that one? Let's do g of f of x. Okay, so that means the g is the outer function, the f is the inner function. So f of x is x plus 2, and so we're going to input x plus 2 into the g function right there. So you're going to get 4 minus x plus 2 squared. Okay, so if you work that out, that's 4 minus, FOIL it, and then when you simplify that, you'll get negative x squared minus 4x. Okay, so that is g of f of x. Okay, and then for part C, they want you to check what is g of f of negative 2. Okay, so now that we've come up with, in part B, an equation for g of f, you can simply plug in negative 2 into this equation. So it's negative 2 squared minus 4 times negative 2, which is negative 4 plus 8, which is 4. Okay, so the end result of the composition function when x is negative 2 is 4. You could also check to see if that's correct by doing it one step at a time. So g of f of negative 2, what you could do is you could start by plugging in negative 2 into the f function, so right here. So if you plug in negative 2 right there, the output would be 0. And then you would take that 0 and plug it into the g function right there. So if you put 0 there, you'd get 4 minus 0 squared, which is 4. So regardless of whether you go through the composition or you go through one machine at a time, you end up with the output of 4. Okay, let's look at this last example together. So they want you to find the domain of f of g, and these are the two functions they give you. Now, a lot of times what you'll do here is you'll start by first finding out what is f of g. Okay, so f of g is f of g of x. Okay, g of x, of course, is radical 9 minus x squared. And if you put radical 9 minus x squared into the f function, you will get radical 9 minus x squared squared minus 9. Okay, so square root and square cancel each other out. So you get 9 minus x squared minus 9. So you end up with negative x squared. Okay, so that is f of g. Right? But if you only look at the final output, negative x squared, you would think that the domain of this function is all real numbers, right? Because you could plug in any value of x here, and it is defined. But that is not the case, because you have to consider the journey that x took to get there. So remember, the journey that x took was that it had to go through the G machine first, get an output, and then into the F machine. So that means that if there are any restricted domains along the way from the very beginning of the journey, then that restriction carries through the entire composition of functions. So since the function began with the G function, right away there is a domain restriction, right? So right away we know that 9 minus x squared has to be greater than or equal to 0. And of course, if you solve that out, that means that x has to be between negative 3 and positive 3. So right away, in the beginning, the domain is x has to be between negative 3 and 3. Okay? Now, after it gets the output into the g function, it goes into the f function. And of course, any number can go into the f function, so there are no additional restrictions. So therefore, the final domain of this function is that x has to be between negative 3 and 3. Even though normally a function that's just equal to negative x squared, the domain is all real numbers, right? But the journey that x had to go through included this function, which does have the restriction on the domain. Okay, so that concludes today's lesson, and on we go.